So section 10.5, page 717, is dealing with independent and dependent events. And again, we're talking about probability of. So when we talk about independent and dependent events, a set of independent events means that the outcome of whatever happens first has no bearing on what happens second. And those have no bearing on what happens third, etc. Okay? So every trial has its own completely unrelated probability to the other event. So now we're talking about multiple events. Now we're not pulling one card out of a deck. We're pulling 2 or 3 or 4 or 5 cards out of a deck. Okay? We're not pulling one sock out of a drawer. We're pulling multiple socks out of a drawer. We're not throwing a die one time or dice one time. We're throwing them multiple times. And we want to find the probability of getting a combination of different outcomes on the multiple trials that we're performing. Okay? So for example, when we flip a coin, it's a fair two-sided coin. If I flip a coin, and I asked you this once before, if I flip it 100 times and I get tails 100 times, what is the probability that I'm going to get a heads on the 101st toss? It's 50-50 still. Does the coin care that it landed on tails 100 times in a row? No, makes absolutely no difference whatsoever. That's an example of independent events, because the first 100 outcomes have absolutely no bearing on the probability of the 101st outcome. Okay, none of them have anything to do with each other. Every one is its own completely separate event with its own completely separate probability. So let's say that we want to flip a coin, and let's say we're going to flip it twice. We want to know what's the probability of getting heads on the first one and then heads on the second one. Well, there's two different ways that you can break this apart to analyze it. One way to do it is think about all the possible outcomes. What's one possible outcome for 2 tosses of a coin? Okay, heads, tails. What's another one? Okay, so tails, tails. What else? Heads, heads. What else? Tails, heads. Any others? Nope. So there are a total of 4 possible outcomes. Of those 4 possible outcomes, how many of them are heads, heads? 1. Now, obviously, this is real easy when we're tossing a coin with 2 possible outcomes twice. But if we were rolling a die 1,000 times, do you want to map out all the different possible outcomes? When there's 6 outcomes for every toss and then 1,000 different tosses? No, we don't want to have to do that. So it turns out that there's a nice easy way to arrive at this, and that is that what we're really doing, guys, is we want the probability of getting a heads and then another heads. These are 2 separate events. And so it turns out that this is equal to the probability of getting a heads times the probability of getting a heads. Because the coin doesn't care. They're independent. So one has nothing to do with the other. What's the probability of getting a heads on 1 toss? 1/2. What's the probability of getting a heads on 1 toss? 1/2. 1/2 times 1/2 is? That's where that answer comes from. So we can find it mathematically rather than actually writing them all out, which is a beautiful thing, because now if we want to toss a 6-sided die 1,000 times, we can figure out what's the probability of getting various different outcomes without having to make a massive diagram. And that's the power of this probability theory, is it allows us to do that. Okay? So what if I wanted the probability of getting a heads and then a tails and then a heads? Well, that would be the probability of a heads times the probability of a tails times the probability of a heads. We're multiplying because this is an and problem. This is really heads and tails and heads in that order. Now, we'll talk in a minute about what happens if the order part doesn't matter. That's a different question, and that'll be the extra thing that I want to throw at you that's actually from section 10.6. We'll do that at the end. So what's the probability of getting a heads? 1/2. What's the probability of getting a tails? What's the probability of getting a heads? 1/2. So the total probability, 1/8. So we have 1 chance in 8. And if we put down all of the different possible combinations of heads and tails with 3 tosses, there'd be 8 of them, one of which would be HTH. That's how that works. Questions about that? So what if now we have a situation where we are going to draw a card and toss a coin? It's a fair 52 card deck. It's a fair 2-sided coin. What's the probability of getting a diamond and a heads? Well, this is going to be equal to the probability of getting what first? No, probability of getting what first? I didn't ask for the number yet. Hold on to the number. A diamond. And means multiply because it's separate events. Probability of getting heads. So the probability of getting a diamond is what? 13 out of 52, which is really what? 1/4. So we have 1/4 times what's the probability of getting a heads? 1/2. So the probability then is 1/8. So 1/8 of the time, 1 out of every 8 trials, we'd expect to get a diamond and a head. So we can combine any kind of events. And again, this is something that actuaries do all the time. Right? What's the probability that a 17-year-old driver who has a 4.0 GPA gets into a car accident where somebody's injured and it costs $1 million? All that kind of stuff they have to think about when they decide how much to charge you or charge your parents for your car insurance, right? All of those kinds of things. Okay? So they have to think of all the different possible combinations and figure them all out and attach some kind of value to them to come up with your monthly premium or your annual premium. It's a lot of work. Questions about that? So the formula for independent events is that the probability of A and B both happening is the probability of A times the probability of B. Everybody got that? Now another common example is this, and this is one I want to point out to you because you have to read the questions carefully. If you don't, you're going to blow these. We're going to draw 2 cards from a deck. After the first card, or I should say we replace the first card this is the key word, before, also a key word, choosing the second card. What is the probability that we get an ace and then another ace? Okay? So here's the idea. This is going to be equal to the probability of getting an ace. I should put an and in here just to keep things consistent. Ace and ace. That's the probability of ace times the probability of another ace. What's the probability of getting an ace from a deck? Okay, 4 out of 52, which is really 1 out of 13. So that's 1 out of 13 times, what's the probability of getting the other ace? 1 out of 13, which gives you 1 out of 169. So just to give you an idea of the chances of that, one divided by 169, it's about 0.0059, or about 0.6%. So just over 0.5% chance. Not very likely, right? We don't even have a 1% chance that would happen. Again, these are the key words. Good question, but these are the key words. We replaced the first card before we drew the second card. That means that there were 4 aces out of 52 cards left in the deck for the second one. Does that make sense? And that's why those are the key words, guys. What we're now going to talk about are dependent events. Dependent events, the outcome of previous events does affect the probability of subsequent events. Everybody understands what we mean by subsequent events? Meaning the events that follow, right? The ones that come later. So here's an example. We draw 2 cards without replacing the first. Okay, before drawing the second. What's the probability now of an ace and then an ace? Well, this is going to be the probability of an ace times the probability of an ace, but we've already drawn an ace out of the deck. Okay? And the way that we symbolize that is we draw a vertical line and then we draw the other ace. What this means is, what's the probability of getting an ace and an ace without replacement? It's the probability of getting the first ace times the probability of getting a second ace, given that one ace has already been pulled out of the deck. Okay? So this says the probability of getting an ace, given that an ace has already occurred. Notice on the independent version, the first ace had no bearing on the second ace because we put it back in the deck. We were back to 4 aces. We were back to 52 cards in the deck. But now the probability of getting the first ace is what? Yeah, let's write it as 4 out of 52 just so we can really see what's happening. But yes, that does reduce down to 1 over 13. And I would reduce it before I did the math, but let's just leave it like this to set it up. Times, now we're not going to put the first ace back. How many cards are left in the deck? 51. This is the key with dependent events, guys, is that bottom number is now going to change. Now, sometimes the top number will change, sometimes it won't. Okay, in this case it will, because it's an ace again, but the bottom number is definitely going to change because it's being impacted by the first event. Does that make sense to everybody? So there's only 51 cards in the deck. Now, on this particular example, how many of those are actually aces? 3, because we never put back the one that we already pulled out. And so this then gives you 4 out of 52 times 3 over 51. Now, if you're going to actually multiply this out, this would be 1 over 13 times 1 over 17, which would be 1 over 170, 200, 221. Is that right? Okay. And so 1 divided by 221 is 0.0045. 0.0045, so that's about a 0.45% chance. Whereas in the independent version, what was the percent chance? 0.6. It's not the same, is it? There was a higher likelihood of this happening if we put the first ace back, because there were more aces to choose from the second time. Does everybody see how that works? Does everybody understand that difference between dependent and independent? A lot of times what it comes down to is the words with replacement or without replacement. With replacement means independent, because you're resetting the system back to where it was to begin with. Dependent means you're not resetting the system, and so now the probabilities of the next events are going to be affected by the first event. Okay, let me give you another example. You have your sock drawer. Actually, you have your clothes basket, dirty clothes basket. Because he can't reach the drawers. In it, you have 6 white socks, 4 black socks, and 2 pink socks. Okay? So this is obviously my sock basket, right? Okay. The infamous sock thief, Bagel, steals a sock. What's the probability that that sock is a black sock? Well, how many black socks does he have to choose from? How many socks total does he have to choose from? 12. So the probability is 1 out of 3. What's the probability that he steals a pink sock? 2 out of 12, which would be 1 out of 6, right? Now, you find the first sock, replace it, and then he steals a second sock. Because that's the way Bagel is. He's a trickster. What's the probability that the first one is blue and the second one is pink? I'm sorry, black and pink. Sorry, I usually use blue when I do this. So, that's going to be, first of all, is this independent or dependent? Independent. Why? Because we put it back. Therefore, we have reset the system. Okay? So we're playing with a full deck again, so to speak, a full basket. So that's the probability of a black sock times the probability of a pink sock. What's the probability of getting a black sock? 1 out of 3. What's the probability of getting a pink sock? 1 out of 6. That means there's a 1 in 18 chance that he gets a blue one the first time and then a pink one the second time. Black one, sorry. And then a pink one. Now, what if and this is the reality of what happens, what if you don't find the first sock? Now what's the probability of getting a black one and then a pink one? Well, now the probability of getting a black one is still, I'm going to use the original numbers, guys. It's still 4 out of 12, right? Sorry. Probability of getting a black one times, now it's going to be the probability of getting a pink one, given that a black one is already gone. So the probability of a black one is the 4 out of 12. How many socks are now left in the drawer? 11. Of those 11, how many are pink? 2. So notice the top number didn't change this time, but the bottom number did. On dependent, you're guaranteed that the bottom number will change. There is no guarantee that the top number will change. Depends if you're choosing one of the same things again or not. This then becomes 1 over 3 times 2 over 11, which would give you 2 over 33. Yes, sir? In other words, he steals the first sock and you didn't find it to put it back before he stole the second one. So you couldn't replace it. So this is the one that's without replacement. Right? The first time, we found the sock and put it back. We saw him stealing it and we grabbed it before he made it out the doggy door. Or before he buried it in the yard. This one, he made it out into the yard and he buried it and we have no idea where it is. We look for it for 45 minutes because we know he stole it, we know he put it in the yard, and we can't find it anywhere. And it's not a very big yard. He's just that good. So the probability became 2 out of 33. Is that bigger or smaller than 1 over 18? Well, let's see. So 1 out of 18, the original with replacement, is about 5.5%, 5.6%. And the other one was 2 out of 33. So notice, guys, there's a greater chance without replacement of him getting the pink sock the second time. Why? Because there's one less non-pink sock for him to choose from the second time. That increases the chance that he'll get a pink one the second time. Yes, ma'am?
Are they going to ask for specific times when you're comparing the percentages of like if this happens?
Typically, that won't really happen. I mean, certainly that could be a question, but we're not really going to see those in here.
Okay.
But obviously, that's a comparison we could do, right?
Yeah. Like, so there aren't going to be like certain times when you prefer the percentages or anything?
Oh, they could. The question could ask you for percentages. They won't typically ask you to compare with replacement versus without replacement. They're just going to ask you to find one. And again, you're welcome to do it as a percent. I'm doing it as a percent just so we can see the effect, because sometimes looking at the fractions, we can't tell whether it went up or down. But on the test and things, it's just going to ask you what's the probability. So you can just leave it as a fraction. That's fine. Mm-hmm. Other questions, guys? Okay. So now the bonus question. And this one you're going to have to think about very, very carefully. If you leave your dirty sock basket unattended for 2.3 seconds, what is the probability that Bagel steals a sock? Now, hold on. You've got to think about this carefully. 2.3 seconds. What's the probability? Exactly 1. That's more than enough time. That thing's already buried in 2.3 seconds. You're never going to find it. Yes, if you leave it unattended, he will steal it. The minute you turn your back, you could turn around and right back again, and the sock is gone with no sign of Bagel, and you never hurt him. All right, because it's 100%. It's absolute certainty. What this was, guys, was a problem to remind you that absolute certainty is a probability of 1, which corresponds to 100%, right? Okay. Any questions about any of that? Oh, well, it happens less now because we try and be really diligent about taking our socks off downstairs. You know, and if you're not going to walk upstairs to put your sock away, you either throw it into the garage. We have a basket in the garage for dirty towels and stuff. You put it in there so he can't get it. Or you just like launch it upstairs, and there's a baby gate to keep him away from the cat food so he can't go upstairs. Yes. That's Bagel right there. That's the famous sock thief right there.
I was saying it
He's got guilt written all over him, doesn't he? Well, this one's guilty of everything else except for the stealing socks. Yes, she does everything else. Dago's the one that steals the socks. Yes. Piper's the one where it looks like a little sweet little angel, but you turn your back and then the devil horns pop out. Yes. Her nickname is Princess, short for Princess Naughty Pants. All right. Yeah, she's the one that's cost us hundreds or thousands of dollars in vet visits because she eats things she shouldn't eat. Piper. All right, guys. I have one other thing that I need to talk to you about today. Oh, I'm sorry. Excuse me. One thing I need to show you and then one thing I need to talk to you about. I never gave you the formula for dependent. So independent is probability of A times probability of B. Dependent, probability of A and B, is equal to the probability of A times the probability of B given that A already occurred. Now, remember with the disjoint and overlapping events, we were able to kind of condense it down to one formula, really? We can actually do the same thing here. The difference between the two is that the probability of B, given that A already occurred, if it's independent, this part right here has no bearing on anything. The probability of B slash A is the same thing as just the regular probability of B. Does that make sense? Because A didn't have any effect on it. So if you're flipping coins, it's 1/2 and 1/2. Right? If it's dependent, whoop, I'm sorry, that's the wrong button. If it's dependent, then this slash A part will have an effect, and the second part won't just be probability of B. So if you just remember this formula, that will remind you that you've got to ask yourself, okay, do I need to adjust anything on that second probability? Are all the socks back in the drawer? Are all the cards back in the deck? Okay? So really, you can just think of it as one formula that takes care of both. Okay, you just have to stop and think about that second probability, and that's all there is to it. Any questions about that? Now, they're going to give you some of those problems where they give you 2 of the 3 numbers, either in this version or in this version, because the book likes to use both. Whatever they give you, you plug in. Whatever they don't give you, you call x and you solve for x. Okay, so don't let that throw you off. You just plug it into this equation and solve for whatever one they didn't give you. It means B, given that A already happened, it means that when we write this probability, this thing had an effect on the probability of B. But I mean, it doesn't do anything mathematically. It means that when we're counting that probability, we have to think more carefully about what goes on the top and what goes on the bottom, because there's been a change. That's all it means. It doesn't mean you divide by anything. That's not what it means. That's your question, right?
Yeah.
Okay. All right. The last thing I want to talk to you guys about comes from section 10.6. And I want to talk to you about this because you see this pop up on standardized tests and things from time to time. And that is something that we refer to as binomial probability. Binomial probability has to do with probability of events when there's multiple events. So we use this for multiple events. We don't do this when there's only one event. You don't use this when you flip a coin once. You don't use it when you roll a die once. The probability of multiple events where there are only 2 possible outcomes. Now, I am going to put possible outcomes in quotes, and I'll explain why in just a moment. But get that copy down. A great example, the easiest example of this is flipping a coin. What are the possible outcomes? Heads or tails. Everything's heads or tails. There's no third possibility. But this can also apply to events that can be thought of as two possible outcomes, even though there may actually be more. Let me give you an example. You roll a six-sided die. If we're looking at the probability of getting, you roll it 10 times. We want the probability of getting 6 fours. When you roll a six-sided die, how many possible outcomes are there? 6. 1, 2, 3, 4, 5, 6. But in this scenario, we can think of this as two possible outcomes. One of them is that you roll a 4. What's the other one? That you don't roll a 4. So all those other outcomes get lumped into one category, and so we only have two categories of outcomes. Does that make sense? And so a better way to do this is to talk about two possible outcome categories. Everybody understand that? This is something that gets used in a lot of different places in math. Okay, it has applications in set theory and various other places as well. When we talk about constructing things called power sets in set theory, a power set is a subset of a particular set, and so every element in the original set, you can either choose to put it in the new set or choose not to put it in. It's a binary situation, a binomial situation. Okay. So, how do we do something like this? Well, here's the idea. The probability of some binomial event occurring a certain number of times. Come on. Because that's typically what happens. We're going to throw the die more than once. We're going to flip the coin more than once. That's going to be equal to the probability of a success times the probability of a failure. But there's some extra stuff that has to come into play. So let's say we're going to do it n number of times. Okay? I'm sorry, we're not going to do it n number of times. We want that many successes. Okay? I'm not going to use n. That's going to make this more complicated. Let me do it this way. We want the probability of success raised to the number of successes power times the probability of failure raised to the number of failures power. This will make sense when I put numbers in, guys. Just copy it down right now. And then you have to multiply it in the front by something that tells you the number of different orders. So let me show you with our example so that this makes sense. Because right now this makes no sense, right? Looks like gibberish. I'll make it make sense. It's actually very easy. Going back to our example, we're going to throw the die 10 times. Sorry, I've got to restart this tablet. It's driving me nuts. This is something that we use with flipping coins, throwing dice, making free throws in basketball, all those kind of things. Winning games in baseball or any other sport. So we say we're going to throw the die 10 times, and we want the probability that we get 6 fours. Probability that we get 6 fours. So here's the thing, guys. A success would be getting a 4. So what's the probability of getting a 4? 1 out of 6, right? How many of those do we want to get? 6 of them. What's the probability of not getting a 4? 5 out of 6. And if we're getting 6 successes, then how many failures are we getting? 4. We need 4 failures, right? Because we're throwing the die 10 times. So if we want exactly 6 successes, that means we need exactly 4 failures, right? If we only have 3 failures, then we didn't get 6 successes. We got 7. So if we want 6 out of 10 successes, we need 6 successes and 4 failures. The question is, how many different orders can we put it in? In other words, success, 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 failure, 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 failure. That's one order, right? But what about success, failure, S, 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 F, F, F? That's a different outcome, isn't it? There's all kinds of different orders that the successes, that the 4s and the non-4s can come in. What about S, S, F, S, 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 F, F, F? That's another one, right? So order matters here, right? So this number in the front is going to take care of the orders. But when we go to calculate this number in the front, does the order of the S's matter? Can I switch these two S's with each other and get a different outcome? No, I have to rearrange S's and F's, but I don't rearrange S's with S's, right? That doesn't change anything. It either is a 4 or it isn't a 4. Does that make sense? So that's why we use combinations, and so the number in front ends up being, how many times are we throwing the die? 10. 10 trials, and we want how many to be successes? 6. If you were throwing the die 100 times and you wanted 38 successes, it would be 100 choose 38. Does that make sense to everybody? Is that something we could punch into the calculator pretty easily? And this will give us the answer. So let's do this. So this gives us 10 choose, sorry, I need to get to the right place. 10 choose 6 gives us 210. And we're going to multiply that by 210 times parentheses 1 divided by 6 raised to the 6th power times parentheses 5 divided by 6 raised to the 4th power. And so what it gives us, guys, is that there's a 0.002% probability of this happening. So for us to roll a 6-sided die 10 times and get 6 4s, there's just over a 0.2% chance. Just over 1/5 of 1%. Pretty small.